get started. It's a pleasure to have Yilong Zhang from Purdue, formerly from OSU.
I'm wearing this.
To introduce variations of Hodge structures.
So thanks for the introduction, and also thank you for Professor Patrick East and Professor Kyoto give me the opportunity to speak here. And I'm very glad to prepare these lectures for Daniel. And I also learned something a lot from this variation. So this talk I will mostly talk about the variation Hodge structures, and so the structure is the following. So our working example is just one parameter family of elliptic curves. That's where the Hodge theory and the variation of Hodge structure starts. And then I will talk about, give you a formal introduction of where is the Hodge structure is coming from, like both algebraically and analytically. And then we will talk about variation of Hodge structure. Where we are going to go back to this working family again, and then we are going to talk about the Griffiths transversality and how is this related to the deformation of complex structures, and in the end, we will sort of say some words about how this leads to the Higgs bundle. That's the plan. So maybe in the beginning, motivating thing is that so motivation is that if we first take a manifold class, and you will learn that there's a classification of a two-dimensional oriented surface, and so depend on genus, and there is just one as a real manifold. So this is genus equal one oriented compact Riemann compact surface. So as a real manifold or topological manifold, there is no difference. Or you wouldn't see that if you just give two tori and have different size, and one is diffeomorphic to the other. However, if we work away complex numbers or work with algebraic geometry, and we're thinking this compact surface differently. We are thinking about this as a Riemann surface. It has some complex structure in it. This complex structure varies, and it is going to tell that if you have a different size of this torus, and they're actually different. So as a real manifold, they're different, but as a complex manifold, so we are treating this as a complex tora. So this is we are just consider C modulo rank 2 lattice. So lambda is just integral lattice generated by say E1 and E2. So here we just think that we have the complex plan, and E1 and E2 are just arbitrary two vectors that are not parallel to each other. So and this quotient give us quotient of lattice give us a fundamental domain, and so our complex torus is sort of trying to do the opposite edge together, and that gives us the torus. So this glue offset edge, and we will obtain this. So this is a you have to mark where you are gluing. So let's say we are gluing along this parallel edge and another parallel edge. So one is going to give you this loop, the other give you this loop. So we can also give a orientation. So here, and let's say here. So then you may ask why for different E1 and E2 and it give you different things. Well, you can we should think about so on this complex torus C mod lambda, and so there is a canonical holomorphic manifold. So holomorphic manifold. So this is just induced from dz. So where z is z is your just a parameter, complex parameter for c, and this thing just naturally induce your quotient. So this dz is defines a class on the Duranko homology of this torus. So let's just call this dz. And in fact, you can so Duranko homology is over R coefficient. So, however, we know that Duranko homology of T, you can view this as like just differential forms you can integrate against topological cycles, and so you can think about that you integrate along the singular homology of the torus, and so let's say we have a canonical basis, and sort of when we take it to dual, and then we also just cancel it out. So
if you want dz to be in there, you should just C, right?
say it again.
If you want dz to be
Oh
in
yeah,
there,
yeah. That's right. This is the point. Yeah, it has to be complex homology. So this tells us we can just integrate so let's give the cycle name. This one is delta, the other is gamma. So this delta gamma is giving you a basis of this lower H1. Z delta, there is some Z gamma, and so can integrate this holomorphic one form against the delta and gamma, and so we have this integration. This is one complex numbers, and this is another complex number. So we got two complex numbers, but really, what matters is rather the sort of the ratio of this. So we'd rather think this as a pair in P1, because that you can choose twice of the TZ and twice of TZ, and this you it's scalar. So we work with projective space. We just model out the patterns of which element of the homomorphic form you choose. So this thing is pretty much unique if you choose different complex structures. So this is called period, and it's very sensitive with respect to the choice of E1, E2. So this is a period of T, and so the upshot is that so it depends on the E1, E2. So this is going to tell you that as complex manifold, this when you choose this E1 and E2, and you actually get something, a pair of numbers, or just a point in T1 which sort of could be different. And conversely, what we are going to see in the end is that this pair of numbers more or less uniquely determine your complex order. So yeah, so that's the, I guess the like a pretty introduction of the motivation of Hodge theory. Are there any questions? All right, so now we are going to go to the abstract nonsense part, so we are going to talk about Hodge structure formally, how it is coming from, and how to vary it. So here, let me talk about the Hodge structure. Yeah, this is. In these talks, we mostly work with complex numbers. So I'll assume that our starting point is a compact Taylor manifold. And if you don't know what this is, and you can just think about this as a smooth projective variety over complex numbers. So it turns out that if you look at its nth cohomology of this compact Taylor manifold, if you so has a so-called Hodge structure. What does it mean? It means that you want to tensor with complex numbers, working with complex coefficient, and then there is a decomposition. So it's yeah. So if you take this as a H1 x cube, and so it's C, and so that means a Hodge decomposition. So this is going to this as a complex vector space. It is going to decompose n0 piece and n-1 piece, and so on, and up to the H0n piece. So each of them are complex subspace of Hn xc, and also you have these conjugation properties. So HP xn minus p. So because this is a complex vector space, it makes sense to take about conjugation. So it turns out this is the same as H minus p. So another way to think about Hodge structure is that instead of looking at the decompositions, we work with filtrations, and that is for the purpose of doing the variation part. So equivalently, so this space admits a filtration, which is called we call Hodge filtration. This is just a sequence of spaces. So Fn Hn. So I'll just for simplified notation, I'll just write down Hn instead of the whole homology. Fn minus 1 Hn and up to F1 Hn and F0 Hn by the convention F0 is just the Hn xc itself. So more or less this filtrations is just taking the direct sum of the first few pieces in the Hodge decomposition. So these filtrations satisfy the following properties. So satisfies. So for first, if you look at the FP and intersect with the conjugations of n minus p plus 1, and this intersection only gives you the 0 plus. And secondly, its direct sum it is going to be the whole space Hn let's say S. Right. Conjugation, yeah. And so to recover the Hodge decompositions, so that's the that's the two conditions. And to recover the Hodge decompositions, you just sort of taking something more here when they intersect. The first step when they are intersecting is non-empty. So it turns out that this HPQ, HP n minus p, you can write as still FP hn, but intersect. You're trying to. Let me see if this. I think it's h and sorry, f n minus p h and taking the conjugation. So if you take this piece and it's going to intersect now trivially, and that's to cover the Hodge conversation. So if you, this is too abstract, and you can think about that our unit curve case. So T is a complex torus, or you can think about it as a unit curve, this H1 of unit curve C, and it is two-dimensional. So you have a one-dimensional subspace called F1 H1 C, and this piece it is going to be spanned by the homomorphic conforms. So this is the span of DZ. Okay, so then so here is some algebraic story where this is coming from. So where does Hodge structure Hodge distribution coming from? So you have to sort of work with the sheaf cohomology. So you have a constant sheaf Cx, and you want to take resolutions by coherent sheaves. So you just map this as a constant sheaf back to this structure sheaf, and then you can take the derivative omega 1, omega 2, and so on up to omega n to 0. So this is this latter piece is called the is what we denote as omega x star is the round complex. So so what it turns out is that so instead of thinking singular cohomology, so you can think about this as singular cohomology. It's we can work with a sheaf cohomology, with constant sheaf, and then this is taking the hybrid cohomology of this round complex. As soon as you work with the sheaf cohomology, you can start to take the implication. Let's we define Hodge rotation. Fp on this complex of sheaves just by truncation. So it's such a you start from originally start from omega 0, and that's the degree 0 piece, degree 1 piece, and degree 2 piece up to degree n piece. And here you just start from 0 and 0 up to the first non-zero piece is omega p, and then omega p plus 1, and omega n to 0. So you just this is our complex fp omega star. So it's a zeroth piece, first piece, and p plus 1 up to degree So that's the Hodge filtration on the complex, and so then we define the Hodge filtration on the homology FPHN to be taking the hybrid homology of the truncated sheaf. So you take the you still take the nth hybrid homology X, and then you take this truncated sheaf. Actually, you're taking this truncated sheaf, and you have a sheaf map from FP to the original complex, and you define formally you define this to be the image of this inclusion map on the level of homology. So. And what happens is that so by degeneration of the Hodge to the round spectral sequence at E1, and this tells you that let's give a name of this phi. So according to this degeneration, and phi is actually injected. So what is really happening is that the piece Hodge filtration at C is literally just this piece hybrid homology of hybrid homology of FP omega star. So I really think in the literature they also call this Hodge to the round spectral sequence. So first of all, if you give filtrations of the complex of sheaves, and you by like a formal machinery, you induce a spectral sequence, and this is a Hodge to the round spectral sequence. But this is also called the Hodge spectral sequence. I sort of treat them as the same. Yeah, so they are just the two names and floating around. So you may ask why it is degenerate at E1. So it's sort of there's an analytic geometry reason. It is sort of maybe you don't like, but it's kind of a Dirichlet lemma. So if you work with an analytic geometry, and so it is a consequence of the like analysis result in the full Kähler manifold. So it sort of depends on the metric. So Dirichlet lemma plus that you have to choose C infinity resolution of the complex. So instead of working with homomorphic these differentials, you work with smooth differential forms. But you can still keep track of these filtrations. So after you do that, and then you can take the global sections because this is there is no higher homology, and you can essentially just taking global section and taking kernel and co-kernel, and so plus Dirichlet lemma, and this shows this generation bar. So yeah, so if you learn this stuff, you wouldn't do this second time again. And you have learned you have learned before, and you just see it once. So another consequence of this degeneration at E1 is that you can sort of give a canonical identification of the graded piece. As this, and as a piece sheaf homology of omega to the m minus p. So this is also so you have a spectral sequence whose grid piece is given by this. So that's also a sort of a
Sorry, the index is
backwards. Let's see. So oh yeah, it is E. Right. So this should be E and okay, so yeah, so this is the part of story for a single Hodge structure. So now let's work with variation of Hodge structure. Let's first work with variation of complex Hodge structures. So this is like X is still just a complex. Sorry. So let me work with B is a base space is a complex manifold, and so this V let's say it is a local system on B. So complex variation of Hodge structure it is filtration on the complexifications of this local system. Sorry, if you start from local system over Z, and then you can tensor with C, but you can also assume that this is already over C. So
Does the end means it's red end?
yeah, I want to say it's in the end it's wave equivalent.
Oh wait, oh, so the lamp will be end.
Wave equivalent, yeah. So yeah, the notation there probably doesn't make sense at this moment. You have a sequence of subspaces F n Vn inclusion to F minus n. So sorry,
What kind of objects are these?
They are filtration by holomorphic subbundle.
So maybe C should be O then?
Yeah. Yeah, you're right. Yeah, so let's see, it's a tensor over C, and structure sheet, and And then we can talk about being homomorphic. This is sort of sequence of these filtrations, and this last space is also by convention is a whole space.
So these are all then.
Yeah. So it is probably serviceable X.
And all these spaces are V end.
Yeah, you're right. Yeah, sorry about that. Which sort of satisfy still the same properties on the like a single Hodge structure. We just working a family. So first one is that this FP. I'll just skip this VN part for simplicity, and intersect with F n minus P minus 1 plus 1 conjugation.
I think you're defining a real rotation structure. I think for this to make sense, V has to have an R structure, right? Otherwise, I don't think you can make sense of that conjugation.
Okay, so for complex variable Hodge structure, there is no such condition.
No, there's some more data maybe. So maybe let's just define an RVHS and I'll
RVHS, okay.
Yeah.
Sorry about that. Yeah, actually, I'm not very familiar with the CVHS. So, okay, sorry about that. That's all right. Okay, so yeah, I guess the setup I learned from is sort of this contribution. Yeah.
Should it be B's instead of X's? Because you said B was the main or like is there B and
yeah.
X?
Yeah, it should be B, yeah, sorry. This is just sort of only give you the zero vector bundle, secondly, and this FP direct sum, and this thing it is a whole V. Structure sheet of OB, and the last condition is rather more important, which is called the Griffiths transversality. So it's going to tell you that. So first of all, this you start from local system. So yesterday we listened to Christian's talk. This local system give you corresponds to this flat bundles. So you do have the working with vector bundles. You do have a flat connection. So it makes sense to talk about the flat connection. So this is your flat connection.
So for the second equality, this is not an equality of holomorphic.
Yeah. Maybe it's this the Dirac bundles. See, Dirac bundle. Yeah. That's right. So nabla from FP, and I think it's going to sense to F P minus 1. And so it's omega B. So what does this mean? So what does this mean? So formally, this is like you have a filtration of homomorphic vector bundles, and you take the derivative, you just get back to the upper piece. But really, from the point of view of just differential forms, so if you just take, say, you take the omega in the so relative division form. I have said that this setup is coming from that I have a deformation of complex manifold. So this is a suppose Vn is coming from geometry in the sense that you have a family of smooth strong family of compact Hilbert manifold. So your V is coming from the Rn afterwards star C. So I guess tensor is C, and this is where this local system is coming from. And so by topology, there's a Ehresmann theorem, which is going to tell you that locally this is just trivial as a real manifold. So this is locally this is just a diffeomorphism to the central fiber and across the base. So here there is no harm to just assume that this is so there is no harm to assume that this is just a homomorphic disk. So you can assume that this is a homomorphic disk. So because we sort of want to study local property of VHS. However, this Collar expansion theory tells you that just as the complex torus example we talked about in the beginning, if you think of a torus as a real manifold, it's just itself. There is no like a moduli of real manifold. But if you think about a complex manifold, it does have a non-trivial variation. So Collar's theory by on deformation of complex structure. By this, the first order deformation. What is a complex structure? You can just think about it. You have like a complex manifold, and at each point in your tangent space, and there is a sort of a rotation of 90 degrees, and this sort of varies in a continuous way, and also satisfies some integrability condition. So that's a complex structure, and Collar theory tells you that you can work with the real manifold, but sort of you should think about the nearby this fiber, other complex manifold. You have to pull back to the central fiber as a real manifold. You need to compare the two complex structures. And so in general, this is very hard to study, but to the first order, it is worked out. So the first order deformation is governed by a 0-1 form in the holomorphic 0-1 holomorphic part of the tangent bundle. So of the central fiber. So this is this Collar-Spencer class, which I just denote the kappa. It is locally some summation alpha beta some smooth functions, and then sort of DDZ alpha, and a tensor with DZ beta part. it's sort of that meaning that you give me you give me one direction. So how does this has anything to do with Griffiths transversality? This is just saying that on the base, this is B, and you choose directions, say ddt, and on the total space, you have this smooth proper family. You lift it up into some ddt part. So this is a fiber X table, and then sort of this Griffiths transversality is really is going to take an omega in the relative and relative differential forms like an x or b, and so which just means that you have some differential forms which on the fiber directions has so on fiber directions you have at least p dzi and so Griffiths transversality is that if you take some differential forms in the total space with restriction of the fiber, is at least p homomorphic in the sense of this Hodge diffusion. And when you take the derivative and you lose at most 1 dzi, so that's roughly what it says. So when you take the derivative, so partial Q dot of this omega, and to the first order you restrict to Q0, and it's literally just given by the cut product with this Polar-Spencer class. So I'll just write it this way. You have to take the class.
This is kind of like mod putting one out by some stuff, right?
So this is a after you're right. So this is equal to the cut product is that after you modulo. So let me write these. So the Griffiths transversality tells you that this class leaving the fp minus 1 and for hn of x. So when the modulo the induced nabla on the graded piece so what you can do is that if you take the fp, so you map to this by this Griffiths transversality, you map it to fp minus 1. But if you take the graded piece, you mod out this fp, and so on the source you are taking sort of the pure piece part, and not in the p plus 1's part. So p plus 1, and then you take the graded piece. So fiber wise, you usually restrict it to 0. By our degeneration of E1, spectral distribution of E1, and this is identified with h x and x0 and omega p, and this is n minus p, and this is in n minus p plus 1 and x0 omega p minus 1 x0, and you have this map, and so let's call this induced left on the nabla bar. So the upshot is that this nabla bar is exactly cut with the Kodaira-Spencer class. So
This is like the method used by applying apple and then pairing with your vector field.
yeah. So the cut product and the sort of doing the contraction kind of thing. Yeah, that's right. So this upshot. The super version is that this nabla bar is you send a class to the sort of I'll first bring in the state. So the car product. You have also to do some contraction thing with this omega 1 with the Kodaira-Spencer class. Okay, so what is this going to tell you? So I will just give you the morality of this story is the following. So what is VHS in a word? So according to this Kodaira-Spencer theory, all I want to tell you is that what we can think about VHS is that you are fixing fix a complex vector space. So let's say it's the nth homology of your central fiber, and you are just trying to vary the complex subspace. So VHS is to vary complex subspace in it. So now back to our original example. Is that family of elliptic curves. So here I choose a very specific family of elliptic curves. I'll choose what is called the Lorentz family. Y squared equal to x minus 1 x minus t. So this what do you can see is that if you choose for different t, and it's going to give you different elliptic curves, it's at 0, 1, and infinity it's going to give you different fibers. So at 0 and it gives you a normal fiber, 1 will give you a normal fiber, and infinity is give you this reducible two components of rational curves. And what you are going to think about this is this dz, like we mentioned in the beginning, for the holomorphic manifolds. So here it is rather has an equation in it. So this holomorphic manifolds in this case it can be written as a dx over y. So that's the more precise way of writing down this holomorphic manifolds. So this is our holomorphic manifolds, and we have talked about that this thing give you the Hodge fixation. So the sort of this particular choose of class, and in H1 of let's say this is our x is this family of elliptic curves, and the base is actually C here. So this is x at time t. So at time t spans the Hodge fluctuations of this. But you should think about this as a complex subspace of a fixed base point. Locally, it's a fixed base point. So let's say it's you have some point t0 is a fixed point, and in a small neighborhood, you are makes sense to talk about this Arrhenius-Mann triangulation. And so this is a contain h1 xt and identify with this h1 xt0. So you're locally you're fixing a single fiber, and you have a like a polymorphic one forms in it, and so when you're changing your elliptic curves, you're changing this thing. This form is changing, and you pair with the you look at the two integrate over delta and gamma, and they're going to be different, and you are varying that data. This is sort of the ratio of that period, and you're varying your homomorphic one forms. You're varying this one-dimensional complex subspace in it. And this is a local variation, and globally you can even think about around these three band fibers, and something is going on falling out here and on here, and sort of this is governed by this Picard-Fuchs equations, where Christian in the first talk about this. So in this case, the Picard-Fuchs equations is a second-order differential equations. If you work it out, it's actually worked out explicitly in Daniel's notes, if you're interested. So it's a Picard-Fuchs equation. And is given by, so let's call this omega t. Let me call this omega t. So is that if you it makes sense to so this equations depends on t. So it makes sense to take the derivative with respect to t. So it turns out that if you take the second order derivative, and it's going to be sort of dependent on the first order derivative and the zeroth order. So it's like this. 2t minus 1. So the fraction part has a denominator t and t minus 1. It means that you have singularities around there, and the numerator part has 2t minus 1. I think this means that at infinity you have something funny going on. So that's exactly telling you that 1, 0, and infinity is the places you have to be careful. Locally, this solution is going to have a logarithmic pole. So by the ODE theory, so locally, let's say around t equal to 0, and you have solutions is given by this ft log t plus some gt, and this ft and gt, there are some particular holomorphic functions, and which you can actually compute it very explicitly, but it requires some work. So the idea is that you can just take the power series expansion and plug in this and the bootstrap. But sort of the zeroth order data, like f0 log t, sort of tell you around t equals 0 and what is going on. So last comment I want to give is that some monotonic matrix I recently just learned from Daniel is that if you just think about this family of elliptic curves topologically, which is like without really thinking about what is Hodge fluctuation And this is already a very interesting question. So because you can, at each point you have this local system Z2, and you go around here, and you go around here, and you go around here, and see what is the monogamy of this rank 2 matrix. So it turns out it's worked out, and so I have to check the. Sorry, I'm over time. So let me just use 1 minute to say that. So the local monogamy matrix of here, one is 1, 2, 0, 1. After the second point is 1, 0, negative 2, 1. And at the last point is going to be sort of a compensation and take the inverse. And is 1, negative 2, 2, negative 3. So this is actually like a, so all these matrices are quasi-uniform. They're actually uniform. If you diagonalize, put this in the normal form, this is 1, 1, 2, 0, 1. And this local monogamy is actually completely worked out by Codara and the norm. And so this is a sort of very classical, and it's a, I guess I was over time and stuff.
That matrix has eigenvalue -1, -1. So you still
Last
need
one is, yeah, it's
because the
minus,
trace
it's
is
not
minus
just
2.
-1, it should be 0.
Yeah, it is -2.
Yeah, so it's -1, -1. So it's not. So it still need a quasi word.
Wait a second.
Yeah, it's quasi.
Yeah, it's still quasi.
Is the surface?
Use again.
Is the surface? It's not.
The surface is actually singular at these two nodal points. You have to resolve it and to get this, and so the local monogamy. So that after you resolve this, you get the neural model. You get a neural model. This Codara's theory tells you that local monogamy is like this and this. Yeah. There it is.
Questions?
Yeah, it turns out that x squared plus y squared plus t squared thing I was saying is true, but the very fact that you can write the